So welcome back again. Good afternoon, everyone. Today we are going to discuss something about the product of two subgroups of a given group. The group may be finite or infinite, but we are going to uh, see when the product of two groups is is a group or in more particular way we can say that that forms a subgroup. Okay. Uh, so we can consider two groups and then we can talk about first product, their product, how we can define the product of the two subgroups. And then after that, what we can talk about the condition under which it itself becomes a group and more particularly a subgroup of the original group. Okay. So for this, let us assume that let G be a group and H and K be subgroups of G. Both are the subgroups of G. Okay. So of course, some may be equals to G also. There is no problem. But thing is that both are the subgroups of G. Then define their product. Define their product H times K equals to HK, where small h belongs to capital H and small k belongs to capital K. In general, if you see, this kind of product is not going to be a group. Okay, you can take some example and then you can check it out. Fine. Maybe closure property, maybe not there. Okay. Of course, identity is going to be there because both H and K has identity, but some property may be missing. Now we will see under what condition this becomes a group. Okay. So there is a theorem or a result we can say that it states or gives the condition for this product to be a subgroup. Okay. So let H and K be subgroups of G, be subgroups of G, then HK is a subgroup of G if and only if HK equals to KH. Okay. This suggests that it means you may sometimes may feel that this is nothing but the condition as we use to say that the group is abelian. Okay, but thing is that it is not like that because when we were discussing about coset, if we are writing A H equals to something B H, it doesn't mean that A equals to B. There may be different A and B for which these two cosets are equal. Okay, and we have seen that what is the condition for this one. And of course, for this we have a result like A B inverse should belongs to H. Okay, so this was the thing what we have uh, discussed earlier in the last class. Okay, so it doesn't mean that a group is abelian, and of course, if the group is abelian, then this is going to hold. Okay, so don't be let us not be confused with this condition as that the group is abelian. Okay, so let us see further how we can prove this one. So proof. So initially let us assume that SK is a subgroup of G. So let HK is a subgroup of G. Then now we need to prove, then we claim, what we claim, HK equality of these two. It means that of course you know that this is a set and this is also a set, okay, and we don't know whether they are subgroup or not, but by assumption we have assumed that that set HK is a subgroup of G. Okay, we need to prove that HK contained in KH, and also we need to prove that KH contained in HK. These two things we need to prove. Okay, so let us see how we can prove. So you know that these containment, for this containment, we need to take some element from here. Then we need to prove that this the element what we have chosen from here, or any arbitrary element which is in HK is also in KH, and similarly here also in the second case. Okay, so let us assume, let X belongs to HK, and do remember that we have assumed that HK is a subgroup of G. So this, and also H and K separately also subgroups of G. So these things need to be remembered while proving. So let X belongs to HK, then X equals to then not like this. We can write then because HK is a subgroup of G, so X inverse should also be in HK. Okay.
HK.
And therefore, because X inverse belongs to HK, so this implies that X inverse equals to some S times K. Okay. For some H belongs to H and K belongs to capital K. It's all right until now. And therefore, X inverse and inverse, that is H times K, inverse of S times K.
Inverse.
So this is equals to K inverse and H inverse by reversal law. And in the left hand side, we have inverse of X inverse. So we have X, and this is equals to X inverse. Sorry.
Inverse,
K
H inverse.
inverse and H inverse. K inverse, H inverse. Okay. So you should remember that because H and K were subgroups of H was a subgroup of G, K was also subgroup of G. Okay. So K inverse should be in K, and this should be in H. All right. So this should belongs to KH. So initially we have selected any arbitrary element from HK, and that element is also now we are able to prove that this element also is a member of KH. So what does this mean? That HK is a subset of KH. All right. So the question is that one may ask that can we proceed in a similar fashion for this? So for this, I think we can say big no, because HK, we have assumed that HK is a subgroup. We did not assume that KH is a subgroup. KH is a subgroup. So similar fashion, uh, uh, the steps in the similar fashion we cannot take to prove other inclusion. Okay. For this, let us see how we can take. Of course, we will be doing something similar. Okay, let us assume. Now let y belongs to kh. Now we need to prove that this y is also member of hk. So that need to be uh, that has to be that need to be our target. Okay. So this implies that then y equals to k times h for some k belongs to capital K and small h belongs to capital H. Fine. So this y can be written as h inverse. We can write k as k inverse inverse of K inverse, and this H we can write inverse of H inverse. Okay. Uh, you know that K, capital K and capital H are subgroups of G, so their inverse also belongs to in that group K and H respectively. Fine. So this is ultimately is going to be a member of capital K, and this is going to be a member of capital H. And initially we have taken this element in KH. So okay, until now it is clear. Okay.
Yes, sir.
Of course, I have not done anything major, but you see, using the reversal law, we can write it like this: H inverse and K inverse belong inverse of this quantity. Is it okay? Uh-huh. Is it
Yes,
okay?
sir.
Hmm. So, you know that this element belongs to capital H, this element belongs to capital K, okay? All right. And we have assumed that KH is a subgroup, you know, because if we are going we have assumed this one, and we wanted to prove these two things, okay? So we can very much use this thing, okay? So therefore, inverse of this quantity has to be in HK, all right, by closure property. So this has to be in HK, as HK is a subgroup of G by assumption, all right. So we have taken some arbitrary element from KH, and that element we are able to prove that is also member of HK. So this should imply that KH contained in HK. So you can name it 1 and you can name it 2. So from 1 and 2, 1 and 2 together implies that HK equals to KH.
PH.
So this proves the first part. Okay, this proves the first part, and second part means converse part. We can for converse part we need to assume that they are equal, and then we need to prove that HK is a subgroup of G. Fine. And you know how to prove that a subset is a subgroup of G. First of all, that need to be a subset. Of course, if H and K are subgroups of G, all right. So their product, this will contain the element of this form, okay. And remember that H and K are also member of G, and because G is a group, so this will be always in G at least. Okay, this will always be in a G. So one thing is very sure that HK should always be a subset of G. Okay,
G.
is it okay? Fine. So this should
Yes,
we
sir.
should remember. And one more thing, from here we may have other implications also. If this is a subset, so number of element in HK, that is in this product, should be less than or equal to capital G. All right. So
G.
yeah. And once this becomes a group, HK becomes a group, it means we have now authority to use the order of group or subgroup. Okay. So order of this, when this becomes a subgroup of G, will always be less than or equals to G. Okay. So these three things you should remember. First thing, this is subset. Second thing, as a subset, number of that is cardinality of HK should be less than or equals to G. And if HK becomes a group, once we prove this result, and you are using this result to prove that some product is becoming a subgroup. In that case, we have very much right to use the word order. Okay, so order of HK is going to be less than or equals to the order of G. Okay. Okay. So conversely, let us see. Conversely, let HK equals to KH. So we now claim what we claim, that HK is a subgroup of Okay. Or because hk equals to kh, so once hk becomes subgroup, then kh also becomes subgroup, because in this case, in this case I'm talking about, not in general, in this case. Or okay, so fine. So to prove that a subset is a, because this is a subset is a subgroup, what tools we have? Anyone? What tools we can use to prove this is subgroup? In Measure we have two. Do you remember? Oh, really, you forgot everything. Two-step test and one-step test. Are you able to recall? Two-step test, that is A, B belongs to HK, we need to prove, and then for any element in HK, A inverse also be member of this. Okay. This is two-step test. This is one-step test is A, B inverse should be a member of HK. Fine. So you can use
Yes.
any of them. Let us use the one-step test for this. Okay. So let us assume let xy belongs to hk. Hk. Okay. Then we need to prove xy inverse is a member of hk using one-step test. So let us see. Okay. So xy belongs to h times k, since so x equals to some hk and y equals to also h1 k1 for some h1 k and k1, and this belongs to h, and these belongs to k.
Okay.
Fine. So xy inverse, let us consider this one. So hk, and then we have h1 and then h1 and then k1 inverse of this. So we can write h and then k, and then we can write k inverse h inverse one inverse k1 inverse h1 inverse. Okay, fine. Okay, let us write like
Yes.
this: h and then k and then k1 inverse and then h1 inverse. One thing, we have assumed that hk equals to kh. Fine. It means if you are taking some h here and k here, then there should be some h dash here and some k dash here. Fine. Is there any problem?
No, sir.
Okay. Don't Please don't think that this hk should be same here. Okay. Fine. This is something a collection of coset, or you can talk about, because when we talk about coset, then we take a single element each time. Okay. And here we are writing h completely. It means we are taking element. Here we take element from group. Here we are taking elements from subgroup. Okay, fine. So this should be the case. So this equals to h k, and then this is of the form something because h and k are subgroups. So this is of the form some k h. So this should be equals to something h prime k prime, something like this. Okay, are you getting?
Yes,
So
sir.
this is equals to some. Let us write h2 and then k2. Uh, Let us. We'll give the reasoning here so that you can. And this is because just a minute. Let me put it like this is because we can write for some K2 and H2. Okay, this is not bar. Please don't be get confused. This is not bar. So we have again HK and then we have H2 and then K2. Okay. Again, you see here these two elements. So for this, we can write KH2. We can write some, suppose we are writing K1 and then, no, not K1, but some H3, huh? S3 and
Yes.
K1. You can write if you are
A2.
not, no, you have, if you have used K1, so we can write K2. Okay. For some
Yes, sir.
H3 and K2. H3 and K2. So this we can write H and then H3 and then K2 and then are we missing something? I think this should be here should be K2. Huh? Yes. Yes, here K2 is there. Okay. So here should be K2 I have used already. So we can write K3. Huh? We can write K3. So here also K2 and then here we can write K3. Fine. So here we have
Yes, sir.
elements from H only. So this is element H4 and we can write this is as K4. So H4 is nothing but H and H3 belongs to capital H and then K4 is equals to K3 and K2
A3, K2 belong to K.
belongs to K. Okay, because H and K are subgroups. So we have written this element in this form H time is some H time some K. Okay, so this belongs to a which set? H times K. Okay, so I think we are done. Or do you have any doubt?
No, sir.
It's okay. Okay, thank you. Uh, K3 and then K2, I think. Okay, K2. So this completes the proof. So now we know when product of two subgroups becomes again a group, okay, or again a subgroup of that particular group under consideration. So this is another way how we can generate more and more groups. So once you have some group, some subgroups, you got two subgroups, you can generate using them another subgroup, and then you are getting another subgroup. Okay, then you can again generate. Okay, समझ रहे हो आप? So this is a way. And now we are going to discuss something important. Uh, Important in the sense that this is going to give us order of product of group. Okay. So once we have subgroup, then we can talk about the order of that particular subgroup or group. So next theorem, and these theorems are important in viewpoint of competitions also. Sometimes in objective questions they ask. Okay, okay, let us see what does it says. So let H and K be finite. You should note it down, finite. Okay, finite subgroups of G. Then order of HK equals to order of H times order of K and divided by order of H intersection K. Order of H intersection K. Okay. This is one of the important results, how to determine. And proof runs proof centered around when we are talking about the product of these two subgroups, it means we are keeping all possible elements of this form. All right. And when we are talking about order of this, in particular as a subgroup, it means it has to be a subset. Okay. But when we are counting only these things, okay, so we may have some repetition. Okay, we may have some repetition. H1, K1 may be equals to something H2 and K2. For H1 is not equals to H2 and K1 is not equals to K2 also. But we may have like this. Okay, so there may be repetition of same elements so many times. So thing is that one thing is very much clear that the product of this is not going to be order of product of H and K is not going to be equals to order of H and K unless all product are distinct. Okay, जब डिस्टिंक्ट अलग अलग सारे प्रोडक्ट हो जाएंगे तब हो जाएगा, दोनों सेम हो जाएंगे, अदरवाइज होने वाले नहीं है. या फिर हम ऐसे कहें कि अगर इसकी वैल्यू 1 हो जाए, है ना, इसकी वैल्यू इंटरसेक्शन का ये जो ऑर्डर है ये वाला, if order of H intersection K becomes 1, it means what? H intersection K equals to the identity only. ठीक है पक्का? तो इस केस में दोनों का प्रोडक्ट सेम, प्रोडक्ट का ऑर्डर दोनों के अलग अलग ऑर्डर के प्रोडक्ट के बराबर हो. पक्का, कोई दिक्कत नहीं?
No, sir.
ओके, सो अब हम क्या करेंगे? We will count, we will count the cosets, okay, and on the basis, and we will remove the repetition in the product. So by considering this, we will prove uh, the order of H and K is equals to the quantity I have written in the right hand side. So let us see proof. Okay, let T equals to H intersection K. Okay, then you know that T should be in K, and T also should be in H. That is should be and also be a subgroup. There is no problem. You can I think you can prove this. Okay, let us see then. I think no. No, the T will be subgroup of G. I've written something. Just a minute. Here should be subset. Here should be subset. Okay. Subset. Fine. I think it is okay. Now let us assume you know that number of coset, two cosets, either they are exactly same or they are totally disjoint. Fine. And disjoint union of disjoint cosets equals that particular group. So this should be remembered. Okay. So we can assume let the number of disjoint cosets, okay, of K in T. This is equals to order of K divided by order of T. Fine. T is a subset of K. Okay. So let us assume this is what we say that M. ये है क्या हमारा number of distinct cosets. Distinct cosets of K in of T in K. Okay. Then K equals to T K1 union T K2 and union dot 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 T Km Ki belongs to capital K. Okay. So let us multiply from left by H. So we are going to get H and then T K1 union T K2 union dot 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 and then T K M. And you know that T is a intersection. T is the intersection of H and K. So T is contained in K and T is also contained in completely H. So every element of T is also a member of H, and H is a subgroup of G. Okay, so if we are multiplying these elements of T and H, then we will be getting some element in H only. Fine. So this means that HT K1 union HT K2 union dot 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 and then HT Km. This is equals to HT because H is a subset of T. Sorry, T is a subset of H. So this is equals to H K1 HK1 union H K2 HK2 H. This is suffix HK2 and union HK M as HT equals to H. Okay, due to this one. Okay, so let us assume that this is a number. Maybe we can write it 3. Now we claim what we claim. We claim that HKI are distinct. ये जितने भी of course TK1 TK2 they were distinct. Fine. So we now claim that they are also distinct. HKI are also distinct. For if मान लेते हैं कि HKI is equals to HKJ for some I and J. ऐसा हो जाता है तो फिर we must have some contradiction. Okay, and also I is not equals to J. ठीक है. So okay, two right coset या left coset equal कब होंगे? This holds, you know, do you remember we proved that AH equals to BH if and only if AB inverse belongs to H. Fine. Using this, we can write KI and KJ inverse belongs to H. Fine. Or K1, KI, KJ are also member of K. But Ki and Kj inverse are a member of K. So Ki, Kj inverse should also member of K. So it means this element is also member of H and this element is also member of K. So it means that, so this would imply that Ki and Kj inverse should be a member of K intersection H. Okay, so it means what? Now again we go to uh, the assumption K intersection H is T. So this implies that Ki and Kj inverse is in T. So this implies that Tki equals to Tkj. Okay, using this result, because this is if and only if kind of thing. Okay, fine. Is it right? It is okay to write like this, or is there any ambiguity arising here? This cannot be, because you know that they are distinct. They are M distinct cosets. So all TK1, TK2, TKM should be distinct. But here we are arriving at that for I is not equals to J or some KI, some KJ, TKI equals to TKJ, which is absurd. Okay, which is fine. So it means that we cannot assume like this. Okay, it means our claim is true. Okay, so now we were at number 3. So let us proceed from there. So now 3 gives hk equals to order of hk1 plus order of hk2. We are able to write like this, just disjoints, sum of this order of these disjoint right cosets, because they are disjoints. Okay, just we proved. So this m, fine, because they are disjoint and they are of course you know that किसी भी कोसेट में, ठीक है ना, उतने ही एलिमेंट होते हैं जितने उस सेट में होंगे, सबसेट में होंगे, ठीक है, ये चीज हमें पता है। तो इट मीन्स व्हाट, h plus order of h plus dot 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 plus order of h. So how many they in numbers, m times order of h, कोई दिक्कत नहीं until now? We
No,
can write
sir.
m and no, not h, but we can write, okay, what is m? M was index of k in t, index of t in k. Okay, so we can write. I don't know. I think I'm missing. Here should be t or k. I don't know. Here should be t or k. You can see it. Okay. Anyway, so this is going to anyway. This is going to be equals to k order of k divided by t. And then this is order of h. ठीक है, कोई दिक्कत नहीं, order of h k, fine.
Yes, sir.
Okay, so what is there? We have order of k, and then we have order of h, and then t is nothing but h intersection k, order of k. Fine. So this proves the result, and you can see I may missing the notation. You can see it. Okay, ठीक है, कोई दिक्कत नहीं. Otherwise it is okay. So we proved this a very important result. Now we will see some application of it, and it has got a many interesting application. In fact, you can very much determine very much determine that how many or what is okay, what is the possibility of a group to have a subgroup of some particular order? Okay, कि एक पर्टिकुलर ऑर्डर का अगर दिया है तो इस ऑर्डर के उसके पास सब ग्रुप होंगे कि नहीं होंगे, अपार्ट फ्रॉम द लैग्रांज थ्योरम। ओके, कि इस ऑर्डर के दो सब ग्रुप हो सकते हैं कि नहीं हो सकते हैं, ठीक है। एंड इसको मैं क्लियर कर देता हूँ, ये यहाँ पे जो मैंने पहले लिखा था वही होगा, के एच होता है, ठीक है, यहाँ पे के एच ही होता है। सो लेट मी करेक्ट इट। के एंड टी, ओके, ठीक है बेटा, चलो। So let us see some application of it. Its corollary, one corollary is there. Let H and K be subgroups of G, and there let H and K both are subgroups of G, and then order of H is greater than square root of order of G. Order of K is also greater than square root of order of G. Okay, then order of H intersection K is greater than 1. That is H intersection K cannot be singleton identity, ठीक है। सो अगर इसका ऑर्डर H और इसके सबग्रुप का ऑर्डर इसके स्क्वायर रूट से ज्यादा हुआ तो ऐसा होगा। सो वी कैन प्रूव दिस, since H and K are subgroups of G, so Obviously H and K should be subsets of G, and therefore the number of elements will be less than that. Okay, and then order of, that is number of elements here. If I'm writing like this, because we are not very much sure that HK is a subgroup, so it means now I'm writing like this. It means I am talking about number of elements. Okay, not order of. Okay, so number of elements in this less than or equals to that of order of G. ठीक है, so this would imply that देखिए order of G, this is greater than or equals to order of H and K. Then now, just now we have proved that this is equals to order of H and order of K, and then divided by order of H intersection K. H intersection K. Fine. But order of H and K is given here. They are greater than square root of G, order of G. So this is square root of order of G 2 times. And then we have H intersection, order of H intersection K. Fine. So in the top, in the numerator, we have order of G, and then divided by order of H intersection K. Okay. So we have a G, order of G is equals to order of G divided by uh, order of H intersection K. Fine. So these two will get cancelled. So we have this means that H intersection K, order of H intersection K should be greater than 1. It means what? किसके intersection में एक से ज़्यादा element. It means that H intersection should have more than one element. So H intersection K cannot be singleton identity. Fine. Okay. All right.
Yes, sir.
Okay. So let us see some application of this. Now the question is that example. So many questions can be made from this result. If G is a group of order 35 of order 35, then so that it cannot have two subgroups of order 7. That is to say that it is given that order of G is 35. Okay, and you can write 35 as 7 into 5. Okay, so both are the prime. ध्यान रहे आप, दोनों prime है. 7 and 5 primes. इसको फिर जनरलाइज करेंगे हम अभी, but let us see here. So कह रहे हैं कि this group cannot have two subgroups of order 7. 5, so that need to be seen. So here, let us assume, let H and K be two subgroups of G, and H and order of K equals to 7. सब मान लिया कि दो subgroups हैं, उनके order 7 है, ठीक है ना, इसके पास दो subgroups हैं. So we must have some contradiction, okay? And also let us make it clear that both are not same. Okay. So H, because H and K are subgroups of G, so H intersection K. Okay. Then H intersection K. You can prove it that is a subgroup of H. Okay. Is a subgroup of H, and also it is a subgroup of K, and more means it has more property. If H, K and subgroup, So this intersection will be contained in H and as well in K. But more specifically, they are also, this is also a subgroup of H as well as K. Okay, fine. So this is a subgroup of H, and you can also write H intersection K is also a subgroup of K. Fine. So now H intersection K, you remember the Lagrange's theorem? Order of H intersection K should divide order of H. Order of subgroups divide order of group. Fine. In a finite group. This is by Lagrange's theorem. By Lagrange's theorem. It means H intersection K, H intersection K की possibility हम देखेंगे, ठीक है ना? तो H intersection K, order of H intersection K, and order of H is what? P. It means what? H intersection K का order क्या हो सकता है? 1 और P. Okay, because divisor, positive divisors of prime P are this P is 7 in fact. Let me write 7. Okay, fine. या तो ये 1 होगा या फिर 7 होगा. So I am saying that it cannot be 1. Here order of H intersection K equals to P, that is equals to 7, and can't be 1 as अगर इन दोनों का इंटरसेक्शन 1 हो गया, ठीक है? नो, just a minute. I think this part. So there is possibility, there are possibilities. Intersection order of this intersection may be 1 or 7. Fine. So here order of H intersection K cannot be 7 because if so, अगर ऐसा होता है तो इसका मतलब H और इंटरसेक्शन K, ठीक है ना? H और इंटरसेक्शन के दोनों का ऑर्डर 7 है, इंटरसेक्शन 7 है, और फिर क्या है, दोनों का अलग अलग भी कितना है, ऑर्डर 7 है, ठीक है? If so, then H becomes K. पक्का कोई दिक्कत तो नहीं? हेलो हेलो
सर.
हाँ, अगर H इंटरसेक्शन के 7 हुआ तो इसका मतलब H और के दोनों सेम हो जाएंगे क्योंकि दोनों के अलग अलग ऑर्डर भी 7 है, ठीक है ना? सो वी मस्ट हैव H intersection K order of this subgroup is equals to 1. ठीक है, कोई दिक्कत नहीं? So now H intersection K order of this is equals to H intersection times H K order of K and then divided by order of H intersection K. So both H and K has same 7 order, so 7 times 7, and then this one is 1, that is 49. So order of HK is or the number of elements in HK is 49. Order of order. I mean to say that number of elements in HK is 49. पक्का? और इसमें हम वो एलिमेंट रख रहे हैं तो जो डिस्टिंक्ट हैं, तो रिपीटिशन भी नहीं होगा, ठीक है ना?
Yes, sir.
So but this is a greater than order of G. ये पॉसिबल है?
No.
नहीं पॉसिबल है ना, because HK is always subset of G, ठीक है ना? अभी HK तो ये हुआ या नहीं हुआ हम नहीं कह रहे हैं, ठीक है ना? लेकिन इसके ऑर्डर की जब हम बात कर रहे हैं, मान लो अगर सब ग्रुप हो गया तो डिस्टिंक्ट एलिमेंट होंगे, तो कितने एलिमेंट हो रहे हैं? 49 एलिमेंट्स हो रहे हैं, जबकि जी ग्रुप का ऑर्डर कितना है? 35 है. सो we cannot have two subgroups of say order 7. Fine. In a similar fashion, now I'm writing this result in a more general form. Up, you can try it to prove. Okay. Suppose G, uh, suppose G is a group of order P times Q, जहाँ पे P और Q प्राइम है, ठीक है, and P is greater than Q, P Q are prime. ठीक है, कोई दिक्कत नहीं. Then prove that G has at most one subgroup of order P. So अभी हम लोगों ने देखा है ना उसमें कि लास्ट एग्जांपल में वी हैव टेकन G is equals to 35 है ना. सो इसको मैंने लिखा था 7 into 5 है ना. तो यहाँ पे P इक्वल्स टू कितना हो गया, 7 हो गया, एंड Q इक्वल्स टू कितना हो गया, 5. ठीक है. सो दिस इज P Q एंड यहाँ पे P इज ग्रेटर देन Q है. ठीक है. तो हम लोगों ने यहाँ पे प्रूफ किया कि इसके पास G के पास दो सब ग्रुप्स नहीं हो सकते सेवन ऑर्डर के. बट in a similar fashion you can try, can G have, can G have any possibility of having two subgroup of order 5. ठीक है. So proof of this is similar, very much similar to that the last theorem we proved. Okay. So I'm leaving it to you. You can try it out. So tomorrow we will discuss another topic. Of course, this was essential for that because we have also discussed the cosets, and then now we are going to talk about normal subgroups and factor group. Okay. So for this, we have set up the background, and we will starting discussion on that.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.